Well, good day, everyone. My name is Vinton Cerf. I'm Vice President and Chief Internet Evangelist at Google, but for today's purposes, I'm a member of the InterPlanetary Network Special Interest Group Board of Directors, and very, very excited to present to you Don Boroson, who is from the Lincoln Laboratories. And Don, I'm not going to try to rattle off all of your very distinguished history. But I do want to tell people why it is that you're here on this program. It's because I had gone to Lincoln Laboratories, to the director there, asking for help, thinking can we possibly get a spacecraft to Alpha Centauri or Proxima Centauri and get any data back? How would we do that, and how far away are we from being able to do it? And much to my surprise, Don and his colleagues put together an extraordinary analysis of the challenges that lie ahead in trying to accomplish that objective. And it was so well done, and it was so relevant to the Interplanetary Network Special Interest Group's interests, which is how do we get communications in space to support manned and robotic space exploration. I thought we should share this extraordinary work with everyone who might be interested. And so Don, I'm going to turn this over to you, and thank you again for leading that analysis and for showing how far away we are from being able to achieve this objective. You know, I'll get even with you somehow, but I'm some 53 dB away from it. So with that, Don, the floor is yours.
Thanks so much, Vin, for that kind and fun introduction, and thank you to the Special Interest Group for inviting me. So as Vin just told you, I spent much of my career at MIT Lincoln Laboratory, and there in my work I helped to develop technologies for doing optical laser communications in the near Earth region, in orbits and ups and downs and near the Earth. But about 20 years ago, my team and I started to think about the related but really unique problem of doing laser communication from Mars or from other distant planets. And that was very intriguing. It was fun. And of course, once you start expanding your thinking in a certain direction, curiosity pushes you to think about even farther expansions. And so, mostly for fun, I started to think about communicating from really, really far away. So my talk today is going to be to try to set the scale of things and point out some of the major difficulties that we've identified that are unique to really extreme distances. And I'm not going to pretend to have solutions for any of these problems, but I hope it will interest you and excite you to think about the hurdles that we'll need to tackle. So I've titled it Communicating Over Extreme Distances, and you'll see what that kind of means. And so here we go. So I'm going to start with this picture, crazy picture, and this is, as I said, what I and my teammates thought about for many years, which is communicating and networking near Earth. And so in any one of these lines, we now have technology. We know how to figure out where you are, where the other person is, how to point, how to connect, make the connection, how to send data, how to make error correction, how to do networking and switching and routing. We know how to do all those things in this picture out to medium kinds of distances. And I really have nothing to add to this, especially in this august body of space internet. We know how to do this, right? But if you start to think about the outer solar system, where I'd like to connect back into that network, but it's pretty much a lone user. It's starting to be a different paradigm. It's the hard work is just getting that link to work at all, and then we have different kinds of protocols to send the data and to hook into the network. But it's mostly about getting that signal back. But what I'm going to talk about today is trying to do it from crazy far away, from a star. And this is completely about just trying to make that signal go from one place to another. So my talk is going to be sort of give you an overview of what links mean over such extreme ranges. Quite a lot about pointing, because it's really all about getting the signal from one place to another. Then I'm going to step back and kind of look at what does a mission like this look like, and how would we get there, and then some concluding thoughts. So as I said, 20 years ago, my team started to look at doing laser comm from Mars. And an engineer wants to know exactly how far and exactly how much everything. And so the range of distances, even amongst the planets, is already such a huge range that you have to look at distances on a log scale. So can you see my mouse here, by the way?
Yes, we can see the mouse.
Great. Okay. So this is a log scale of distance, and it's not from the sun. This is from the Earth, because Earth-centric. So here's geosynchronous, which is essentially 40,000 kilometers from the center of the Earth. The moon is 400,000. The Lagrange points are 1.5 million. The planets here are out at hundreds of millions to billions to almost 10 billion kilometers. So this is a log scale of distance. Distance in log scale is sort of funny to think about, because if I have a rocket and it goes really fast to here, it's going slower on a log scale. It's hardly moving here. So we'll come back to the trip later, but a log scale of distance is sort of, you have to think about it. And so this is a light second a minute. This is how long it takes light to go this distance. So here's a light day out here. And we're going to be interested in doing things from the Earth to these kinds of places. And so we're interested in sending power with the communications in it. So first we're going to talk about power, and sending power from one place to another. There's something we call a link budget, and the link budget is how much did you start with, and then what's the gain of the transmitter, and then how big is your receiver, and then there's terms having to do with wavelength and the range. And for a fixed power and a fixed transmitter and a fixed receiver, if I can deliver a certain power between them at one distance, if I push the other end of the link farther and farther away, the power, because of diffraction, the power goes down as the range squared. So on this, I've shown these are 10 dB. Engineers, we like to think in dB. So if I go a factor of 10 in distance, then the power drops a factor of 100 or 20 dB. So this curve then, this is this range squared curve, is kind of a constant difficulty of sending power, because it's the same design. One design does this curve. Okay, so that's for power, but I'm really interested in communications. And we in the communications industry know that if you do everything right, you can deliver a data rate that's proportional to the power. And that's because every bit that you get has to have a certain energy in it. And so this is now a log scale of data rates. And so if I can deliver 100 megabits per second here, if I go a factor of 10 farther away, it's only 1 megabit per second. It drops by a factor of 100. So this curve, this kind of a curve, kind of shows us the difficulty of doing communications, because if I want to do something that's out here, those things, something about those things had to get bigger, either the power I transmit or the size, the apertures, or something has to get bigger if I want to move to the right. All right, so this is sort of a tutorial. Where does technology sit today? Well, for really, really long distances, NASA has the Deep Space Network, and they have antennas around the world. They have 3 main places where they have 30-ish meter antennas, and at each one of those places they have a 70-meter antenna, which is just really huge. The kind of terminals that they sent to deep space, to Mars, for instance, are several meter dishes and several tens of watts of power. And so this is the Mars Reconnaissance Orbiter. In fact, that's still circling Mars right now, the NASA machine. And talking into one of these big dishes. So Mars, of course, sometimes it's close and sometimes it's far from the Earth. And when it's close, it can do a few megabits per second. And when it's far, it can do half a megabit per second. And so it falls on a nice curve here. What's interesting is that this curve kind of sets the limit of the deep space network at all, because even 50 years ago, 45 years ago, the Voyagers were sent. And as you know from reading the paper, the farthest Voyager is way past Pluto now, and it's sending a little more than 100 bits per second from its 3.5 meter dish and a couple tens of watts at X-band with old technology, but still it's kind of on this curve. So it's 100 bits per second. So as I said, my background is in optical, and I'm going to sort of motivate why we do optical in another log scale chart. And this is log of frequency in the electromagnetic spectrum. And so here's 1 gigahertz and 10 gigahertz, 100 gigahertz, 1,000 gigahertz, called the terahertz. We don't really talk about petahertz. We talk more about the wavelengths. And so here's the bands that are well known, of course. Cell phone and Wi-Fi is down here, but satellite communications is between about 5 and a few tens of gigahertz, different bands in the SATCOM band. And here's where the optical bands are. Visible light is about a half a micron wavelength, and the fiber optic to your home telecommunications is about 1.5 microns. And so you can see that there's a factor of 10 to the fourth approximately shorter wavelength in the optical band. And as I said before, in that link budgeting, there was a term there about wavelength, and it turns out that the beam that comes out of an antenna has a certain width, which is proportional to this wavelength. And so for a very short wavelength, the beam comes out very narrow, which means that it's very focused into the far field. In fact, this 10 to the fourth gain in wavelength in each of the 2 dimensions of the beam suggests that I should be able to send power 10 to the 8th times more efficiently for fixed apertures. There's a caveat, though, in that the energy here, each photon, if you will, has more energy in it. And so for every watt, there are fewer photons here than there are radio photons here. And so we call that quantum noise, and that's sort of a penalty of 10 to the fourth. Nevertheless, going from here to here for the same power and the same apertures, I can send signal to noise ratio about 10 to the fourth times more efficiently. And so if we're going to try to do communicating from really, really far away, that 10 to the fourth, we'd like that in our pocket. So I'm going to just presume that we're going to do some kind of optical communications when we go, if we go to a star. So this motivates why we're going to optical. Of course, this beam is very, very narrow, so keep that in mind. So here's this curve again. So where do the optical technologies fall? Well, the longest laser comm link so far was several years ago, the Lunar Laser Comm Demo. And it was a NASA MIT Lincoln Laboratory project for which I was the principal investigator. And we were able to do from the moon to the Earth about 600 megabits per second. So, it's not as good as the line for the deep space network, but we didn't need to be at it. No one needed a terabit per second from the moon. And so we did this design, and here's some pictures of what the hardware looked like. It was a 10 centimeter telescope. A telescope is an antenna for lasers. So that's how big that is. It's only 4 inches and only a half a watt. And from that to a ground terminal, which we did it in 4 smaller terminals, but they were equivalent to a 0.8 meter diameter receiver. So from 10 centimeter to 0.8 meter with a half a watt, we were able to do 622 megabits per second from the moon. And so this is what a diagonal line, if I sent that farther and farther away, I could have delivered power such that if I had changed my modem electronics, I could have done a lower data rate down here. Well, as I told you 20 years ago, my team was looking at the Mars project, the Mars link. And in fact, that study that we were doing and the initial work that we're doing was between Lincoln Laboratory and Jet Propulsion Lab. And the JPL has continued to work on that technology. And I'm going to show you some of their pictures. They have a program called the Deep Space Optical Comm, and it's they're well along, and they hope to fly that in the next year or so. And it's going to fly on the so-called Psyche mission. Psyche is an asteroid that they're going to go visit. And of course, it's bigger, so they can do better here. So they have a bigger aperture, 22 centimeters and 4 watts of power. But the main difference is that they're going to talk to a big receiver, the Hale telescope Palomar, 5 meters. And so their diagonal line is kind of over here. And so they worked hard to beat this Deep Space Network line just to show that you can do better than that. Of course, one could do much, much better, but this is where they are. So that's an intro to where we stand today. Okay, now let's roll up our sleeves and say, where's that star? Well, it's here. It's about Alpha Centauri, and it's really a group of stars. And the closest of the group is 4.2 light years, which is pretty darn far, even on this log scale. The two bright, and I'm going to talk some more about what this group looks like, but the brighter stars are a little bit farther, 4.3 light years away, which in dB on this, on the diagonal line here is about 0.3 dB harder. So, but anyway, so here it is. It's out here. And so, as I said, if I wanted to do technology and go in this direction, something has to be bigger, something has to be better. So what I'm going to, for this talk, I'm going to postulate, let's try to do 1 kilobit per second. And of course, you can say, well, who needs that? Let's do 100, just to show. So here's where the kilobit per second is over here. And with respect to this diagonal line, that's 73 dB. So that's 20 million times more capability of something, more power received. More difficult to send power that far. Okay, so we're going to need to figure out how would we make 20 million times higher capability. But first, I do want to tell you one little digression on, remember I told you that the data rate can be proportional to the power that received. And so the proportionality constant, we call that the efficiency. And the most efficient way to send data turns out to be, just about the most efficient way, turns out to be sending what we call orthogonal signals. And it can be a pulse. So this is, I'm going to send 1 pulse out of 16 different time slots. And these are called orthogonal because if I were to make a measurement here, I wouldn't see any of this. So that's zero in the cross correlation between those two signals. This would take a transmitter that can store up its energy and send big pulses, but we kind of know how to do that. And you can see that if I have 16 time slots, 16 corresponds to 4 bits. I can also do orthogonal in frequency. So I can send one pulse and then 1 pulse, but this pulse is at 1 color and this pulse is at another color. This also has an orthogonality property. And turns out that you can see this takes a lot of bandwidth, and this is way faster than the data rate. So it takes a lot of bandwidth to do this, but we're going to be at such slow data rates that asking for lots of bandwidth more than the data rate isn't the problem. And so the way these work is at my receiver, I measure this time slot, this time I measure each one separately. And in optics, we're going to use noiseless photon counting. We have such things, and they can measure quite efficiently down to single photons. And in frequency, I can measure this tone and this tone and this tone. And each one of them is looking for photons. And you can see what's interesting is that if there's no noise, if I receive a single photon here, then I know which of the 16 time slots it came in, and I got 4 bits for my 1 photon. So I can do multiple bits per photon. And in fact, if I put coding and I do all the other signal processing tricks, I can actually get n, in this number here, bits per received photon in either of these two things. And so, and the bigger n is, the more time slots I have, the more efficient I can get. And some people have done as high as 10 or 10, even a dozen. So on Lunar Laser Comm, we did pulse position modulation. We did 16-ary. And so that suggests that we should have been able to do up to 4 bits for every single photon that we received. Of course, we made engineering trade-offs, and we did it at 2. So we were able to get 2 bits per every received photons, and we demonstrated that. The JPL DSOC is also going to do 16-ary, but they're going to experiment with even larger M's. And so I think if we're going to do sometime in the future to go Alpha Centauri, we're going to pull out all the stops and do hundreds, thousands of tones to try to get the highest efficiency that we can. But just remember that I'm kind of working at fewer than 1 photon per bit. So keep that in mind. So now I want to do some accounting and try to find out where can I make up 73 dB? Where can I get that factor of 10 million? So this is a simple little budget, if you will, of the JPL DSOC system, and they had 22-centimeter transmitter and 4 watts and 5-meter receiver, and I'm presuming here that they did 2 bits efficiency, even though they could have, if they had 16-ary, they could do 4. We're going to say they had 2 bits efficiency, and I'm going to call these 0 dB. Each one of these is 0 dB because I'm looking for a factor of 73 dB more over this. This is not a complete link budget. Any real link budget has lots of implementation losses and all kinds of other details, and they could be as much as 10, 15, maybe even 20 dB implementation losses. But I'm just going to keep these major engineering challenges of how big is the space aperture, how much power, and how big is the receive aperture. Okay, so there's a million ways to make up 73 dB. I'm going to pick one, and I'm going to pick one with these parameters. I'm going to say, let's try to send a 3.5-meter telescope to the star. So the Hubble's 2.5 meter, 2.4 meters. So this is bigger than the Hubble, but that's kind of what it would look like. It would be a big telescope like that. I'm going to presume that I can make a kilowatt of transmit power when I get there. And I'm going to presume that my receiver on the ground is 40 meters. And it turns out that the European Space Agency has plans to do a 40-ish meter receiver on the ground. So, and then I'm going to, as I said, I'm going to try to do highly efficient communications of a very high number of orthogonal signals. And it turns out this is one way to get 72 or 73 dB. And we'll talk later about what our other choices are. Can I move these numbers around and keep the 73 dB? I can also point out that the wavelength, if I went to a shorter wavelength, I can do a little bit more efficient to the tune of a few dB. And that'll turn out to be a question of technology and if I'm going to go through atmospheres and such. But so here's a point design, and we can follow this along. I'm going to use these parameters to see what would a system like this mean to try to make this work. So this 3.5-meter telescope as a transmitter sends a very, very narrow beam. And that's why we do it, because it's very focused and allows me to deliver, 24 dB more power than their 22-centimeter one. It's very, very narrow beam. But now I have to point that narrow beam if I really want to make use of it. And I have to point it to within a fraction of how wide it is. So what you're going to see. So let me tell you what that means. So here near the Earth, if I want to talk to between two terminals, and they're moving with respect to each other. So let this be me, and let this be the guy I'm trying to talk to. So I'm going to need to point at him and send my power to him. And maybe I can do that just with my GPS. But the beam is very, very narrow. And typically what we do is try to see him, either the light from him or his image, and then point back with respect to where I think he is. So if this is where he is, or she, and she's sending me light, and I see the light from there, but it takes light a certain amount of time to go that far. And in fact, if he's going in a straight direction, a straight path, he's really here by the time I see that. And remember, I'm going to want to send my light so it gets to where he's going to be, and he's going to be here. So from my point of view, I see him here, but I need to point blindly in this direction so that he gets my light. And we call this the point ahead. And for a linear motion like this, the point ahead, you can sort of see from the geometry here, in radians, it's V over C. So 2V over C. So this could be a few tens of microradians. There's 5 microradians in an arc second for those who know that. So it could be a few tens of microradians. For things moving really, really fast, it could be hundreds of microradians. But this is, and this is what most of our systems do today. They sort of calculate this and then point blindly out here. It is possible that if I point blindly and if I do poorly, I can do a protocol with him and jiggle things around and have him correct it with some feedback. If I move it and he says, you know, you moved, you went down, he sends a signal to me, and I can correct my pointing. Now let's look at trying to do it from a star, right? So here I am at Alpha Centauri, and here's the solar system. So if to try to take the same approach, if I see an uplink from the Earth, or I see the Earth itself, it takes light 4.2 years to get here. And then I need to point back to where he's going to be 8.4 years after that, because it took 4.2 and another 4.2. So the Earth will have gone around 8 times from where I saw it the first time. Furthermore, I have motion that I'm moving here too. There's another vector of calculation here. So you can see it's already starting to be a little complex to point this narrow beam and hit the Earth 8 years after where I saw the Earth. And just so you know, Alpha Centauri is in the southern hemisphere from the Earth, and it's not straight up; it's at 60 degrees. And so this is looking at the south pole of the Earth, going around like this, and you can see the 60 degrees. So let's zoom in and see how accurately I can do this. So here's kind of a sort of to scale picture. Here's the Earth-Moon system. Remember, I'm trying to point back to the Earth and Moon. Here's the sun. And can look up in any table and find out that the Earth moves about 30 kilometers a second around the sun, which is 2.6 million kilometers a day. So now back to that design that I proposed, the 3.5 meter telescope. If I can get it to be a diffraction limited performance, and suppose I'm using the same wavelength that I used in my lunar mission, 1.5 microns, then the beam's about a little less than half of a microradian. So you can calculate that at 4.2 light years away, it's 17 million kilometers across. So this is kind of the size of our spot. And you can see that with the Earth moving this fast, the Earth would move through that spot in about 7 days. So I better point my beam to be plus or minus 3.5 days, or 3.5 degrees, if you think about the orbit circle, I need to hit it to within 3.5 days. And the beam took 4.2 years to get there. So the first thing I'm going to need to know, not only all these motions, but I need to know exactly how far away I am. I need that to know that to about 0.2%, is 4.2 light years. Otherwise, I'm going to miss, and I'm going to point over here, and he's going to be here. And I think we can pretty much state that there's no feedback. He can't tell me you missed, because it's an 8-year round trip, and he'll be long gone. So this is all open loop. I have to hit that spot with my narrow little beam. You might ask, is there also motion of the solar system and the Alpha Centauri system with respect to each other? That's called proper motion. And I looked that up, and it seems to be much smaller than this motion. So the main motion is the Earth going around the sun. So I kind of need to know all these motions and all these positions. Let's take another look at this. So suppose I'm looking at the sun, and I'm towards the viewer in this out of plane. I'm closer than the sun here, right? So let's take a look at what happens here. So here's planets going around the sun, and you can sort of see that the sun will illuminate the planets fully when they're on this side. They'll be nearly full circles. It's a 60-degree tilt, but there'll be nearly full circles of light. And I kind of have a chance at seeing them. But remember, these are exoplanets. These are like seeing exoplanets, the same way as from the Earth, I try to see exoplanets around other stars. So here I am at Alpha Centauri, and I'm trying to see or point towards exoplanets. And so they'll be illuminated over here, and maybe that will help them to be visible from my 3.5-meter telescope at Alpha Centauri. On this side, though, this is towards me, you can see that the sunlit side is away from me. And I'm going to mostly see the dark side of the planets, and maybe I'll see little crescents of light, and that's probably not bright enough to be seen. So here's the Earth going around here. Maybe I can see him when he's here. I probably can't see him when he's here. So if he's over here and I can't see him and I still want to point, I'm going to need to look at something else that is well lit, that tells me with respect to some marker with respect to which I can point. So maybe I'll look at Jupiter, or maybe I'll look at the sun itself. When the Earth is over here, it's too dim to be seen. As a note, so over here, you think, okay, that's good. That's the good spot because I can see the Earth over here. But remember, I'm trying to send a downlink to him. So if I'm in the Earth over here looking up at Alpha Centauri, when I'm over here, Alpha Centauri is in the daylight. I'm looking past the sun to see Alpha Centauri in the daylight sky. So if I'm doing this from the Earth's surface through the atmosphere, that's sporting. It's pretty difficult. And I'm going to talk about that more a little bit later. So there's a question of, well, gee, when I'm trying to see Alpha Centauri past the sun, shall I just give up on this 6 months and I'm only listen when Alpha Centauri is in the nighttime sky over here? A lot of questions to be asked about pointing and where the extraneous light is. So those are big numbers I showed you there, 3.5 meter and a kilowatt. Maybe we should lower our sights. Instead of a kilobit per second, let's just do 1 bit per second. All right, so now I only needed 40-some dB efficiency. So I'm going to shrink my transmitter to a little over a meter. And instead of a kilowatt, I'm going to ask for 10 watts. I'm going to keep the stuff at the Earth the same size, so in efficiency, why not? And so that would seem to be simpler. Maybe it's easier to send a 1 meter telescope to the star and only get 10 watts when I get there. But remember, I'm now trying to do 1 bit per second. And as I showed you before, the efficiency I'm looking for is on the order of a photon per bit. In fact, fewer than 1 photon per bit, really, but let's call that 1 photon per bit. So to do 1 bit per second, I'm trying to receive 1 photon per second, actually less than that, from Alpha Centauri. So there better not be any extraneous light, like from the sky or from background, to the tune of 1 per second. There better be 1/10 of that or 100th of that. And when I showed you that half the year Alpha Centauri is in the daylight sky, that's almost impossible to keep scattered sunlight to down to 1/10 of a photon per second. So that'd be very, very difficult. So, gee, maybe we should move our ground terminal to being out in space where I don't have atmosphere, or on the moon or something like that. So, boy, the cost just went way, way up. But maybe that's the way to do it. So now suppose I kept it on the ground, but I'm only in the nighttime. Well, I'm still trying to, in this 1 bit per second, I'm still trying to keep the background light to be way less than a photon per second. And so I now have to worry about all other sources. Even Alpha Centauri itself is going to be probably in my field of view, and I need to consider it. And there's stars behind it that are going to be sending more than 1 photon per second. So the good news of low data rates is that I can make things be smaller and simpler. But the bad news is that it's really tough to keep the signal to noise ratio high enough to do such links. A little bit on an uplink, I'd kind of like to be able to send a message to it for commands or something, maybe not, or certainly for pointing. But so here's a simple calculation. I'm going to keep the 3.5 meter in space. I'm going to send 1,000 watts on the uplink. I have no problem making power on the Earth, so I can do that. But up through the atmosphere, I had my 40-meter receiver here, but I didn't need that to be diffraction limited, really. I can do photon counting even with stars twinkling, even with atmospheric turbulence. But on the uplink, I'm trying to have my transmitter give a diffraction limited, nice focused beam. And we know how to do adaptive optics, but no one's really done it great on a 40-meter. In fact, even 10 meters is quite sporting to try to transmit that. So I'm going to lower my sights here and do a 10-meter uplink aperture with very good diffraction limited adaptive optics, or maybe even put this in space where perhaps I can do that for a low enough cost. Once again, if I go to a shorter wavelength, I can maybe pick up a few dB or do a little bit better. But so the uplink seems not to be that difficult. But let's look at the pointing for the uplink. So for the uplink, this is the group of Alpha Centauri. And there's one, the closest one is called Alpha Centauri C, Proxima Centauri. And it's a few degrees away in the sky, away from the other two, which are brighter. And these two are the brighter and easier ones to see, turn out to be, they orbit each other. And with an 80-year orbit, it's been deduced. So the angle between them changes to the tune of a few tens of microradians, but it's changing all the time. Now, this is a few degrees over here. So if I'm going to send a rocket to one of these places, when we do that to Mars, halfway there, it opens up its camera, it takes a look around, it goes, I need to scooch to the right a little bit, and it changes its trajectory. It's unclear, I'm going to talk some more about this later, but it's unclear whether we're going to have enough power, any power, halfway to open up and look and do anything and change a rocket. So there's a very good chance, I think, that we're going to need to open loop, shoot straight, and just hit this thing. So that means that these are moving around an 80-year orbit, and they're this looks close together in the sky, but these are are hundreds of millions of kilometers apart. So I'd kind of like to know where I'm going to send my rocket, and I might need to just point straight and hit it straight. So I better need to know where the rocket's going to be when it gets there. So let's zoom in at one of these. So here's Alpha Centauri A, for instance, and it's known to be 1.5 million kilometers in diameter. This one, as I said, has a couple planets. Right now, they think maybe one of these has a planet. Maybe more will be discovered. But those are a couple 100 million kilometers away. And our uplink from that 10-meter aperture that I talked about, and here I'm going to use the DSOC uplink wavelength, is about 4.5 million kilometers. So I need to point my uplink to sort of this kind of accuracy, and that means I need to know, so these planets are moving and the two stars are moving with respect to each other. I'm going to need to know all their motions as well as the motion of my spacecraft well enough so that I can hit this 4.5 million kilometer spot and make sure that my satellite is somewhere in there. And this is all open loop. You can't feed back and say you missed, try again. So that sort of shows you the difficulties of getting power there and figuring out how to point the light. Let's take a step back and what does it mean to have this mission at all? And all those things I just told you about pointing, they're really, really hard. Probably in some future engineering technology, we'll be able to do it. They'll be expensive, but they're doable. But I need to get there. I need to build it. I need to fly it. I need to do the trip, and then it needs to work when it gets there. So let's take a look at time. So now this is this log distance, but now I'm going to do log of time duration, and these are about speeds now. So to give you a sense of speeds, the Earth, we know it's a 150 million kilometer orbit from the sun. It takes 365 days to go around that. So it's going just under 1 billion kilometers per year. That's the speed of the Earth. So just to keep that in mind. So here's one spacecraft. This is the Orion spacecraft. And you can see, and this is the Orion spacecraft is what the humans are going to go back to the moon in the next year or so. And it can go up to about 30,000 kilometers per hour. So at 30,000 kilometers per hour in a year, it would be here. And in 10 years, it would be here. And Alpha Centauri would be crazy. It would be 1 million years or something. Here's the Voyager spacecraft. And thanks to the fact that it zipped around some big planets and picked up some speed, it goes faster, 60,000 kilometers per hour. Still crazy amount of time to get there. The fastest rocket that humans have ever made is actually up there right now. It's the Parker Solar Probe. And what it does, it goes and it gets really close to the sun and takes pictures of the sun. And it's hot there, so it zips around past the sun and then cools off, sends us pictures home, and then zips around again. And when it's zipping around the sun, it's going very, very fast, 692,000 kilometers per hour. So it's the fastest rocket thing that humans have ever made. And okay, well, we're getting close here. We're under 10,000 years if we flew that to Alpha Centauri. But I wouldn't want to wait that long. So let's presume that we can come up with a technology that would take 100 years. And that would have to be just under 50 million kilometers per hour. And that's 66 times faster than the fastest thing humans have ever made. So let's presume we can do that. It's 100 years to get there. And just so you know, at that speed, it would have gotten to, if it did that right from the beginning, it would be at Pluto in a week, right? So it goes through the solar system in a week. and takes 100 years to get to the next star. Of course, that also means that at that next star, it goes through his system in a week too, less than a week. So that's a goal. Let's see what implications this has. By the way, here's where the speed of light is. Takes 4.2 years to get to Alpha Centauri. I didn't talk about it at all in this talk, but there's actually a group called the Breakthrough Starshot group, and they are seriously thinking about sending many tiny little spacecraft on solar wings, if you will, that they're going to push with photonic energy. They're going to send gigawatts of laser power at this sail and push these tiny spacecraft, this is the concept, out to Alpha Centauri. This is not sending 3.5 meter telescope. These are tiny, tiny things with tiny, tiny amounts of power, but they're trying to work this out. It's a completely different solution than what I talked about here, but they're seriously trying to do it. They haven't solved the question yet of how to do it and how to communicate. So they're actually shooting for that, but we're going to shoot for this 100-year one. And just for fun, this is where humans run. This is a marathon run that runs over here. So just to give you a sense of on a log scale of speeds. So circling back, in this point design that I've invoked, I got a 3.5 meter telescope, bigger than the Hubble. The pointing, I'm going to pull out all the stops and see what I can see out there to figure out where to point. I've got no feedback to help me, so it's all open loop, pointing ahead to things that are moving in circles. Very complicated. I'm going to invoke a kilowatt of power. Lasers today are not 100% wall plug efficient. They're 10 to 30%, maybe 50% wall plug efficient. That means I would need to make several kilowatts of power in order to make this laser work. And all those extra watts of power get wasted, the heat. So I'm going to have to be very careful about the design of this big thing that I'm going to send to a star. I've got a big aperture on the ground. That's just dollars. I do have to worry about daytime operations. The 40 meter that the Europeans are building does not point near the sun. So a lot of questions about how big can I really make it? Maybe I need to put it on the moon. The comm efficiency, I think we know how to do that. That's just technology. That's just fast and wideband systems. So this kilowatt, maybe I'll have solar panels. So remember, after it leaves the solar system and it travels for 100 years and then gets to Alpha Centauri, there's nothing in the middle. There's no star giving me power in the middle. And so I have no power input for 100 years. And then when I get there, in a very few days, I go past the star and then I'm gone. So I better, it would be nice if I could slow down when I get there to try to use the power from Alpha Centauri to power myself. But that's going to take control. I don't really know how we're going to do that. If I had lots of power to run my power system, I could see, oh, there's Alpha Centauri, change your trajectory and try to loop around and do tricks with gravitational orbitology, but I don't know how to do that. And that, by the way, that 100 years, it's cold. And even if you would say, well, why don't you just go to sleep, and they wake up every once in a while. Well, guess what? That waking up power means that takes energy too. And that's going to be tricky to find. And so I need to figure out, am I going to be frozen for 100 years? Do I go to sleep? If I go to sleep, where's the energy come to turn back on? Very, very complex question about power. In fact, that's the main motivation for the Starshot people. And by the way, even for this 100-year mission, you have to think back and go, electronics at all have only been invented 100 years ago. And so no one's really ever designed electronics that are going to survive for 100 years, especially in space. So big open question for what is this? Certainly there's redundancy, but I wouldn't even know where to start. Designing electronics, designing everything to last for 100 years in frozen conditions. So that's sort of my thoughts on this. If I want to do this point design where I have a big telescope like the Hubble, I'm going to need to send it on a huge rocket going 100 times faster than any rocket that's ever been built before. We don't know how to do it, and it'd be very expensive. And I have no idea how to do orbital dynamics to slow it down when it gets there. You know, if we're going to build this big thing, we'd be crazy not to try to do science on the way, and then science when we get there. And guess what? Every time you say, oh, I want to invoke something, I want to measure something, that's more power and thermal control. Don't know how to do that. You know, the 100 years I talked about electronics, are there organizations that'll still be around in 100 years? So yes, the United States is still around after 100 years, but organizations come and go. So unclear how that would work. And you know, to be honest, as I said, it was a point design. This 3.5 meter with 1,000 watts was just a 1 point. Maybe there's another way to find 73 dB. I think we would probably re-optimize everything, maybe a much bigger ground terminal on the moon with smaller in space. But we'll need to figure out what's the drivers. Is it the mass to try to go that fast, or is it the power because of the frozen for 100 years, or the cost, whatever is the main driver. As I said, probably we do for something smaller to send there and a big Earth terminal. And as I said, the Breakthrough Starshot are thinking about a lot of tiny transmitters. So I've come to the end, and you know, is there a summary statement? You know, and I looked at this, and it was done for fun, but it's a tough problem. I think it's highly unlikely for this mission to happen, at least in the next many decades. So thank you. Those are my random thoughts on communicating from a star.
Well, hi, Don. It's Vint. I'm going to have to jump off in a couple of minutes for another conference call. But I just love the nuts and bolts that you presented us with and the challenge that it implies. I hope that that we find some solutions. Especially, I think we're more likely to find solutions on the propulsion side. But the harder thing that you keep pointing out is that there's no feedback loop of any reasonable character for adjusting the system. And so it sounds almost as if we have to play a game of probability where we sort of waggle the beam around and hope that we're somewhere, you know, we reduce the effective data rate because we won't get some of the signal, but some of it may show up. So coding will turn out to be important. Some probabilistic pointing may have to be done. It's just such a wonderfully hard problem, but thank you for making it so real for us. Others may be able to stay, but I'm going to have to jump off. But super thanks again for taking the time to bring the IPNSIG group up to speed on where we are with this, which is far from a conclusion.
Thanks, Vin. Yeah, I'm happy to take any questions. Yeah, of course, make the beam narrow and waggle it around, or just spread it in the first place. We do those trades all the time. That's why I said this was a point design. Yeah, this before we set off on a 100-year mission, a lot of analysis will have been done.
All true, and you'll be helping us do it, I'm sure. All right, I'm going to dash, but thanks again so much for taking time. I'm sure this is not the end of the story, it's just the beginning.
Okay, so we do have one official Q&A question from Alberto Montilla. He asks if the dark side of the moon would be a good location for a transmitter receiver for this. You mentioned that space is a potential location, but it really ups the ante on the costs. And any thoughts in particular about the dark side of the moon?
Well, people call it the dark side of the moon. What I think they usually mean is the far side of the moon.
Right.
But as you can see, we're not, at least what I think, we're not constrained by signals coming from the Earth, but the sunlight. And so I want to be where it's dark. So if I go on the moon, then it's in the dark for 2 weeks, and then it's in the sunlight for 2 weeks. So, in a 100-year mission, plus or minus some several percent, do I want to, I think in following up on Vince waggling it, I think what you could do then would be send data and then 2 weeks later, send it again, just in case the receiver was in the sun the first time. But remember, I just told you that if I'm going this crazy fast, I've gone through the whole solar system there in 1 week. So I'm not sure we'd have energy 2 weeks later. So it sure looks like you get a very few days, unless we can change the orbit when we get there and then go into orbit around Alpha Centauri. Wouldn't that be nice? But I don't know how to slow down after going 100 times faster than we've ever gone before with no fuel. So my sense is that from this analysis, we'd have to do it really, really quick.
And really, really perfect.
Really, really perfect. That's right, with no feedback.
Let's see. In chat, someone was asking if nuclear power would be a feasible, power source for, the journey.
Yeah. So, I'm not a power and thermal person. My sense is that the answer is no. Otherwise, this breakthrough starshot people would have invoked that. I think they've kind of done some analysis that suggests that any kind of power source that you can invoke just dies after decades.
Yep. Oh, we do have some answers. More questions coming in.
Good.
Well, some repeats on the nuclear power issue. Can using gamma or X-ray bursts improve your signal level as opposed to optical bands?
So as I said, there's a wavelength term in the efficiency, and yes, the shorter the wavelength you go, the more efficient you can use the aperture. But it's the aperture size I have to fix, and then as I make the wavelength shorter for that aperture size, I get higher and higher directivity. But I just finished telling you that even for the directivity of the optical band, it's already really, really tough to point that correctly. And at the even shorter wavelengths, the beam's even narrower. And so the pointing would have to be even more exquisitely done.
Yep. And then a question, solar wind propulsion has been mentioned. In what stage is that of development?
So again,
unfair question.
Well, so I mean, the breakthrough starshot people they've published things. You can go read what they've done, and as I said, their idea is to have these little solar sails and to send billion-watt lasers up from the ground to push them to 10 or 20% of the speed of light. But boy, there's a lot of technology there of making the billion watts into with an array, and then making that array be coherent, so all billion watts hit the little sail, and then pointing the sail. You know, I can't just sort of go in that direction in the sky. It's got to be to microradians, and that the sail has to be able to catch, you know, to accept the billion watts that's hitting it and not melt. So there's a lot of work, but you can go read what they've worked on. That's kind of why I said let's do it in a standard way with a big telescope and a big rocket, which we don't know.
Okay, and someone's asking, is that project from JPL? I think they mean the breakthrough. Yeah.
So no, the breakthrough is it's another organization and has famous people on it. I'm sure you can go find them online. They have a big board and they have a lot of people working on technologies, but that's a whole other different approach to trying to solve this problem. The JPL, they're doing the DSOC mission out to the Psyche asteroid, and they also have a lot of things you can go read about their mission and their technology.
Okay, thanks. We'll work up a list of links and suggested links, and I'll run it by you, and then we can put it up on the website. One final question: what are your thoughts on having several spacecraft acting as a relay?
You mean halfway between? I guess that's what that means. You know, people often talk about, well, so far, what if I have one halfway? And I've never seen a solution where that comes out to be the better thing to do. So, you know, if one's at Alpha Centauri and another one is halfway Alpha Centauri, that halfway one still has 50 years of path in front of him. And remember, he's now in a place where he has no energy source. Exactly, he needs power. So I don't know how that would work. So my sense is that no. As I said in those very first charts, this is all about getting the power from one place to the other with as focused as you can, but focused means I really need to point it exquisitely.
Okay, we're about 7 minutes over. I think just maybe one more question.
Okay.
What kind of frequency selectivity is practical when we are talking about single photon detection?
Right.
Seems important for both SNR and FSK demodulator.
Yep. So as I said, for our lunar lasercom that we did have superconducting nanowires, what they're called. You can go look those up. And they have quite broad frequency acceptance. And then so what you would do is take the light that you catch from the telescope and you would send it to a bank of filters, a bandpass filters, and each bandpass filter would have at its output a photon detector. So, you know, if I had a 1000-ary frequency shift keying, I would have 1000 detectors, each behind a bandpass filter. And, you know, we're already pretty close to technology that can do that now with photonic integrated circuits, ways to do that. That's not a problem. But each detector would have a broadband, but you would put a filter in front of it, just like in radio systems.
Okay. Well, we're now almost 10 minutes past. Yeah. I think we're going to wrap it. Thank you so very much. It was kind of made your head spin, but very engaging, and it's really motivated me to want to follow up and understand things better.
Great.
And I hope that's a common reaction. So for the participants, we anticipate getting presentation materials up probably within a few days. And again, I talked about some links for suggested further reading, and just really want to thank you, Dr. Boroson. It was really a well done, fascinating presentation.
Great, glad you liked it. Thanks, everybody.